Okay, so let's take a look at example 1. Here we're asked to calculate the volume below the paraboloid, so 9 minus x squared minus y squared, and above the annulus, where x squared plus y squared is between 4 and 9. Okay, so first of all, this function can be written as 9 minus x squared plus y squared, like this. And also the region that we're integrating over is an annulus. And so this is a good candidate to use polar coordinates. So we want to set up our double integral. Again, we're trying to integrate 9 minus x squared plus y squared. So to set up our integral, let's take a look at this region here, right? So again, we have the change of variables for polar coordinates, right? So where x equals r cosine theta, y equals r sine theta, and x squared plus y squared is equal to r squared. So in particular, x squared plus y squared equals r squared, right? So here we have r squared is between 4 and 9. So just putting it into the description of the region R, you get r squared is between 4 and 9, and just taking the square root, you get 2 is less than or equal to r is less than or equal to 3. So what this says is that here we have an annulus where the inner radius is 2 and the outer radius is 3. Okay, so this is what our region looks like. Okay, so so we want to set up our integral. Right, so again, we already know that r goes between 2 and 3, and this is the whole annulus. So theta, the angle theta should go between 0 and 2 pi. Right, so this is following the description of the annulus we gave in the previous page here. Okay, so so we can write down the integral, right? So the outer integral should be for theta, so that goes between 0 and 2 pi. The inner integral is for r, so that goes between between 2 and 3. And then again, we have to convert the x and y variables to r and theta, right? So x squared plus y squared is r squared, so this becomes 9 minus r squared, and then also the dA should be r dr d theta. Right, so this is r dr d theta. Okay, so so we want to calculate this integral, right? So first let's just distribute this r. So what do we have? Integral from 2 to 3, and then this is, so again, I'm distributing the r, so you get 9r minus r cubed dr d theta. Okay, so this is just a polynomial in r. So here, when I take the antiderivative, right, so I'm integrating with respect to r. When I take the antiderivative, I get 9r squared over 2, and then minus. I'm increasing the power, right? So r to the 4th over 4, evaluated from 2 to 3. Okay, so now to calculate this integral, I need to plug in the endpoints, right? So the top number goes in first. So this 9 times 3 squared over 2 minus 3 to the 4th over 4, and subtract. And then I plug in the bottom number, so 9 times 2 squared over 2 minus 2 to the 4th over 4. Okay, so what is this equal to? So let's just calculate this to make things easier. Right, so what am I calculating here? Okay, so this is the calculation, right? So 9 times 3 squared over 2 minus 3 to the 4th over 4, and then this is a minus 9 times 2 squared over 2, and then minus minus becomes a plus, 2 to the 4th over 4. Okay, so hopefully I entered the calculation correctly. So what do we get? I get 16.25. Let's put in the form of a fraction. So this is equal to 25 over 4. Okay, so this whole thing calculates as 25 over 4 d theta. And now this is just an ordinary integral with respect to theta. So the antiderivative of a constant is the constant times the variable, and I need to evaluate at the endpoints. So here just plugging in 2 pi, 2 divided by 4 cancels out, so you get 25 pi over 2. Okay, so this is the calculation. So let's just calculate this as a decimal answer just in case. So we get 39.2699. So let's just round it up to 39.27. Okay, so so that's what we get as the calculation of this integral. And so let's just quickly try to sketch what the volume we're trying to calculate is here, right? So so here the graph of the function is supposed to be a paraboloid. However, the region that we're integrating over is an annulus, right? So you imagine in the xy plane, you have sort of your annulus here. So that's the region that we're integrating over, and then on top of that we have this paraboloid, right? But because this center region is being cut out, you have to imagine that that's not going to be part of the paraboloid, right? So basically we're cutting the center out, and so you imagine the sort of paraboloid goes up, but there's a hole again of radius 2 cut out by the center of the annulus, and so again I'm trying to draw in 3D, but the sketch is not so good, but this is sort of the idea, right? So you have a sort of a paraboloid opening downwards like this, but the center of radius 2 here is being drilled out of the paraboloid. Okay, so that's what this volume represents.